In this episode of Remote Trigonometry, we will be discussing polar coordinates. We're used to Cartesian coordinates where we locate positions by moving left and right and up and down from a starting position of the origin, 0, 0. So for example, kind of like, blocks in a very organized city, I could go 7 blocks to the east or 7 blocks to the right and then pause and then move 4 blocks north, and I would locate the point 7, 4. Or I could go 5 blocks to the west or 5 blocks left and 12 blocks north or 12 blocks up, and I would be at the position -5, 12. Or I could go 10 blocks to the left and 3 blocks down or south, and I would be at the position -10, -3. Notice that we start sort of over here where both x and y are positive, and that is considered quadrant 1. And then we move over to the quadrant where x is negative but y is positive, and we consider that quadrant 2. Where x and y are both negative, we consider that quadrant 3. And then where x is positive but y is negative, we consider that quadrant 4. So we have this sort of natural rotation around the grid in that direction. I point that out because polar coordinates locate positions not by walking on rectangular grids, but instead by recognizing the space as radiating out after you've rotated a certain angle. And so when we measure our angles, we will be measuring by rotating this way as the positive direction. If we chose to rotate down into quadrant 4 first, which is clockwise, we would consider that a negative rotation. With polar coordinates, we still picture ourselves starting at the origin, 0, 0, and to locate positions, what we do instead is we imagine rotating a certain amount. So, picture starting off with yourself facing east or facing down what was the positive x-axis, and picture rotating to a certain direction, kind of like you're a little robot. You're just gonna twist around to a certain direction. Once you position the correct direction to head, then somebody's going to turn your motor on and you are going to head out to your position on a straight line at the appropriate angle. That is what polar coordinates are about. Polar coordinates are about locating a correct direction to rotate and then emanating out in a straight line along that correct angle. So if I wanted to still get to the point 7, 4, I would need to rotate this appropriate angle. Well, as good trigonometry students, we can figure out that angle because I can see that this side of this right triangle is 7, that's the x, was 7, and this side of the right triangle, which is y, was 4. So I have a right triangle that is 7 by 4, and I can use inverse tangent to help me find that angle. Alright, so inverse tangent of, again, opposite is the 4, the y, over the adjacent, which is the x, and I don't know, usually when we're talking about angles like this, it's best to be in degree mode, so I know I'm in degree mode, but you don't have to be in degree mode. So we get in degrees an angle of 29.74. Okay, so 29.74 degrees rounded to the nearest hundredth is the correct angle that I would have to rotate to head out to that point. Well, now I need to know how far to go. Well, once again, recognize that you have a right triangle and the one side was 7 and the other perpendicular side was 4, and so the length is going to be the square root of 7 squared plus 4 squared, or approximately 8.06 when we round to the nearest hundredth. Okay, so again, given a little wiggle room for rounding, if I started at the origin and I rotated so that I was facing now 29.74 degrees, and then I started my motor running and I went a distance of 8.06, I would land at that same point as 7.4. Now let's look at some points that are in some of the other quadrants, okay? So here's -512. The idea stays the same. We're still going to picture ourselves rotating the correct direction. So I'm still going to start facing down the positive x-axis, and I'm going to rotate around until I'm pointing in the correct direction. And then once I'm pointing in the correct direction, I will get my motor running and I will head out to my point, -512. So I still want to find this angle, but notice a little more thinking has to be involved, but it's still thinking we're capable of doing because we're good trig students. The angle that I really want, okay, the angle I really want is this angle, and I can see it's more than 90 degrees, but my coordinates are actually forming a right triangle over here in quadrant 2. So let's use that right triangle. Okay, so this side is a length of 5, this side is a length of 12, and so if I use my calculator, and again I'm in degree mode, the y was a length of 12, the x was a length of 5, and I get an angle of 67.38 when I round to the hundredths place. All right, so that is this angle here, 67.38 degrees. That's not the angle that we want to rotate, because 67.38 degrees would land me over here in quadrant 1. However, if I take 180 degrees and I back off the 67.38 degrees, I will have the correct angle that I want. Okay, so 180 minus 67.38 is 112.62 degrees. So the correct angle to rotate is 112.62 degrees. So again, pointing down the positive x-axis, I'll rotate around. Now I need to know how far to go to land at that same point. Pythagorean theorem is going to help us out, and the one side was 5, so 5 squared. The other side was 12, so 12 squared gives me exactly 13, because 5, 12, 13 is one of our Pythagorean triples. So I have to go exactly a distance of 13 to land at that point. Looking at a point in quadrant 3, again, the idea doesn't change, okay? So I would rotate around so that I was pointing in a direction where I would head off into quadrant 3. So that angle would be an angle, some angle like that. I can see it's more than 180 degrees. So let's think about how we're going to get it. The coordinates are giving me the information about this right triangle here, okay? So this side is 10, that's the x. This side is 3, that's the y. And so the length of 3 for the opposite and 10 for the adjacent will give me 3 for the opposite, 10 for the adjacent will give me 16 point, why don't we just round that to 16.70. All right, so this angle right here is 16.7 degrees. Now, I'm not going to rotate 16.7 degrees from here, because once again, that would land me in quadrant 1. I want to rotate all the way through quadrant 1, all the way through quadrant 2 into quadrant 3. So a half circle, 180, plus the 16.7 is the angle that I really want. So 180 plus 16.7 gives me 196.7 is the angle that we would rotate to land at that point. All right, so 196.7. Now the distance that I would have to go is still the hypotenuse of a right triangle, and so the one side x was length 10, so 100. The other side was length 3, so 3 squared is 9, and I would have to go a distance of 10.44. So a distance of 10.44 would land me at that position. So we have these 3 example points, and we've talked about how to get to those locations with this idea of rotating and moving. So those are the 2 pieces that we're using as our data for our points. We're not using sideways and up and down, x and y. Instead, we're using an angle and a distance that we're radiating out from the origin. So these points are then labeled as not x and y, but we label it as the correct radius. So in this case, it was 8.06 was the correct radius, and then the correct angle. And the correct angle for this one was 29.74 degrees. So we list a radius and we list an angle. And you assume that the angle is measured from the positive x-axis. Okay, so the 0.74 in Cartesian is equivalent to a radius of 8.06, 29.74 degrees in polar coordinates. My point over here, my negative 512, that point in polar coordinates had a radius of 13, and it had an angle of 112.62 degrees. So those are its coordinates in polar coordinates. And then my point down here in quadrant 3, negative 10, negative 3, in polar coordinates, it had a radius of 10.44 and an angle of 196.7 degrees. Those were the polar coordinates for that location. So notice here that xy gives way to a radius and an angle. So these are the polar coordinates. And you really reason out how to go back and forth between the two by using your knowledge of right triangle trig. You use the Pythagorean theorem, you use your right triangle definitions of, in this case we were using tangent, but honestly you could use sine and cosine if you found your distance first. You could do that. But there is some sort of standard notation that we point out. Notice that the x here is the adjacent side of the triangle to that angle, and y is the opposite side. And so cosine of theta is equal to the adjacent over the hypotenuse. So the radius, in this case it was 8.06, times cosine of the angle, which in this case was 29.74 degrees, equals that x coordinate. Alright, so radius times cosine of theta gives me the x coordinate. And if I take sine of the angle, sine would be the opposite side, or the 4, over 8.06, which was the hypotenuse. And if I rewrite that equation, I get 8.06 times sine of theta equals the y coordinate, which was 4. So radius times sine of theta equals the y coordinate. And then the radius the connection between the radius and the x and y, the radius is always the hypotenuse of your right triangle, and so it is the square root of x squared plus y squared. And that's true even when your points don't form right triangles. Like, for example, if I pick this point right here on the x-axis, which is 5, 6, 7, 8, 9, 10, 11, so it's the point 11, 0. If I put 11 in for x and I put 0 in for y, it's still true that the radius is 11. I mean, that's what the radius is in that case. The radius is 11. And if you follow your formula here, it is still going to work. Now, the angle, if you're in quadrant 1, then it is true that your angle is always inverse tangent of y over x. But if you're in these other quadrants, I would basically make sure that you're picturing where you are and making sure that you're getting the right angle. You're much better off trying to picture and understand than to necessarily memorize. Because remember, your calculator is programmed only to give you angle measurements between negative 90 degrees and positive 90 degrees. So if you're over here in quadrant 3, it's not going to give you the correct inverse tangent value. Instead, you have to think about your location. So that's why I was emphasizing the lengths and not the positiveness and negativeness of the coordinates when I was finding the angle. And I instead was finding the correct angle in the right triangle and then reasoning out what the angle would be from the positive x-axis. Okay, so we do have these relationships. If you are in quadrant 1, then this will be true, that inverse tangent of y over x gives you your theta. And it's always true, no matter what quadrant, that x is equal to r times cosine of theta and y is equal to r times sine of theta. That is always true if you get the right angle. And it's always true that your radius is equal to the square root of x squared plus y squared. Let's get a little bit more practice. Let's look at the point 6, 2 as x and y, and let's convert it to polar coordinates. So we have the point sketched out there, and the radius is going to be the hypotenuse of that right triangle, so it'll be the square root of 36 plus 4, or the square root of 40. And I'm just going to leave it in exact form. If we do want to clean it up a little bit, 4 is obviously a multiple or a factor of 40, and so I can factor out the 4 and I get 2 times the square root of 10, and we'll leave that in exact form. Now the angle is this angle here, and 2 is the opposite side, and 6 is the adjacent side. And we will go ahead and round this, but inverse tangent of 1/3, because 2 over 6 reduces to 1/3, gives me 18.43 degrees. If you do convert that to radians, it is approximately 0.3217 radians if you want to answer in radians. Okay, so in polar coordinates, the radius is 2 times the square root of 10, and the angle is 18.43 degrees. That's my radius, that's my angle. Again, you could use the radian angle if you wanted to. If I were given the point 2200 degrees already in polar coordinates and I wanted to go back to rectangular coordinates, the x coordinate, due to right triangle trig, will end up being equal to my radius is 20 times cosine of my angle of 200 degrees. So if I take 20 times cosine of 200, I get negative 18.794. And notice I'm in quadrant 3, so x should be negative. Y is equal to the radius times sine of my angle. So y will be approximately 20 times sine of 200, negative 6.840 is my y coordinate. And so my x and y then are negative 18.79, I'll round to the hundredths place, and then negative 6.844 for the y. So x and y, both negative because I'm in quadrant 3. So then my third example here, so here's my first example answer, here's my second example answer, x, y. My third example, we are in polar and we're going to convert to xy. Again, you can be in radian mode, you don't have to be in degree mode. So here I was given a radius of 16 and an angle of 2 pi over 3. And so x will be 16 times cosine of 2 pi over 3. And because we are good trig students, we automatically know that cosine of 2 pi over 3 is negative 1/2, giving us an exact value of negative 8. And y is equal to 16 the radius times sine of 2 pi over 3. And sine of 2 pi over 3 is the square root of 3 over 2, which is 8 times the square root of 3. So x is negative 8, I'm in quadrant 2, x is negative, y is 8 times the square root of 3. There's my x, there's my y. Alright, so that's a little introduction to polar coordinates, and we will be using them off and on, and we'll then talk about how to create graphs and equations with polar coordinates.